Today, we're going to be reviewing not only the inverse functions, but now we're going to do transformations of those. So, one of the things, I just went over this with my other class, I think I had said it correctly with your class, was the difference between tangent and cotangent. Maybe this is a good warm-up thing to think about. Tangent is in black over here. So what I'm saying here is tangent goes from negative pi over 2 to pi over 2, and it's got a positive slope. The reason why it goes from negative pi over 2 to pi over 2 is we have y over x. Where is x equal to 0? Well, it's equal to 0 at pi over 2. If we go back to the next one, it would be negative pi over 2. We could have went to 3 pi over 2 as well. But anyway, I took the negative pi over 2 to pi over 2 as being my main one. It's got a positive slope. It's going to go, if I go halfway there, I go up 1. If I go halfway back, I go down 1. That's how that works. Same thing for cotangent, except it's got a negative slope, and the interval that we would have a full, nice, continuous piece of the graph in one full period would be from 0 to pi. So it's actually shifted over, and it's got a negative slope. But other than that, it's really pretty much the same general look. You still have that center at the midline, concavity up, concavity down. You're going to go over 1 halfway, and you're going to go up 1. Go over halfway, and you go down 1. So that's just the general idea. And I was trying to go over that with them because I messed that up. Now, what's going on with the sine wave with the transformations? We have lots of transformations going on here. We have A being negative 3, or A amplitude is 3. There is a reflection. So yes, there is a reflection because it's negative. That means it's going to flip it over the midline. It's like a reflection along the midline. B equals 4. What does that mean? That means the period changes from 2 pi to 2 pi over 4, which is pi over 2. That means it happens a lot faster, like 4 times faster. Instead of having one full cycle in 2 pi, now we have a cycle in pi over 2. It's happening a lot quicker. Our phase shift, which is a horizontal, I'm going to call it a horizontal shift. I think it's more descriptive. Phase shift, horizontal shift, is going to be to the right pi over 2. And for some reason, there was a problem that I was helping people with today with the transformations of the inverse functions, and they wanted people to write this as y equals negative 3 sine of 4, parenthesis there, 4 times x plus a negative pi over 2. Actually, they didn't. They just wanted that minus pi over 2. I got that on my mind. Never mind. See you too. That part. So let me ignore that last little bit, just a little bit about how we write it. We're saying that we just use the negative 3 to do our amplitude reflection. We use 4 to come up with our new period. We use the minus pi over 2 to get my right pi over 2. And then my vertical shift is going to be based on that plus 2, so it's going up 2 spaces, up 2. That's it, yes.
What's the reflection?
Reflection, we normally have a wave like this for a positive sign. The reflection, since it's a negative value, that negative 3, negative sign is going to be like this. It's reflected across that midline. Reflection, yes. I just wrote reflection, yes. Amplitude is 3. Reflection, yes. We do have a reflection. Instead of being the normal positive, now we have the negative sign. And then the period is pi over 2. Horizontal shift of pi over right pi over 2. And then vertical shift is up 2. And that's, we're coming up with, what does the A tell me? What does the B tell me? What does the C tell me? And what does this D tell me? So A, B, C, and D. This was from A. This was our B. That gave us, therefore, we got this period. And this was my C. This was my D. So, yes. Pause for a second. Okay, so let's get into this again. Bless you. Just a review. Amplitude, how far up and down it goes, how far off the midline and above the midline and below the midline. Frequency will then let me know what the period is. Don't forget that's 2 pi over b. When it comes to sine and cosine, for tangent it's pi over b. Phase shift is the horizontal shift. And then vertical shift, I'm just going to let it stand as it is. That's what we're doing. Horizontal shift, I typically think of as opposite. If you want to write it as a minus something, then it may give you exactly what it is, positive or negative. Positive to the right, negative to the left. In my mind, it goes opposite, so if it's minus something, it's going to go to the right. Plus something, it's going to go that far to the left. Okay, so that's just general thoughts. Here, now, when we're talking about cosecant, they chose cosecant to use as our example. I want us to consider the parent function in both cases. They graphed it here both times. They have this. That didn't work for me. That's a stay, trying to straighten itself out. So these parent functions, that's sort of like the before. As one of my students mentioned, they thought that that's the before. And then we have the after is this, where we moved off. It doesn't want to do what I want it to do. But nothing's changed other than the amplitude. Well, what do they mean by that? Well, I always like to think of the fact that this is that inverse of cosecant is sine. So I even draw in sine sometimes just to bring up what's happening. That would be the sine wave. Now, if I drew, now that it's y equals 2 times cosecant, well, how does that relate to y equals 2 sine x? Well, that would be like this. And I would continue to go on like that. It's the amplitude here is 2. Amplitude here is 1. We've changed the amplitude now. You can see how the green relates to the blue that I've drawn, and the pink or chartreuse, whatever you want to call that, that pink color is relating to the black. And every time they hit a midline, an asymptote crops up. So we still have our asymptotes at negative pi, 0, pi, 2 pi, and so on. And that's every time it hits 0. Every time it hits the midline. If we start having vertical shifts, that midline is going to move up. But every time the inverse of cosecant is sine, if I draw that sine wave, every time it hits the midline, the asymptote is going to crop up. Questions on this? Now, if I look at that same idea with a compression where I'm actually making the amplitude less, I have, gosh, it does not like me drawing short curve. Here we go. Let's just look at those two. What does that have? What happens there? Well, it goes ahead and it comes down closer to that midline. It's going less off of the midline. It's only going half instead of a full unit off. So compression and stretch. This is a stretch, and this is a compression. The amplitude was compressed and made it go off the midline less. Stretch, it made it go off the midline more. Questions on that? I'm just coloring in, just sort of comprehending what that would look like. And again, I always have the before the parent function, the after we do that compression or stretch. The next one, I already have drawn in a little bit. B is going to, this B, we started off with the parent function in blue. Remember my period here for this, the period is equal to 2 pi. Now when I go to, when secant 2x, b is 2. Here b is 2. So now my period is going to be divided by 2. 2 pi divided by 2 is pi. So this, the full interval, let me see here. This interval is pi over 4 to 5 pi over 4. Pi over 4 to 5 pi over 4. This interval here was pi. And again, what we normally have is our regular period is 2 pi. Now I've sort of dissected what's going on with the frequency here on the first one. Questions about that? The next one, I'm going to go ahead and now the period is 4 pi because I'm going to divide by 1/2, which is like multiplying by 2. I end up with 4 pi. So this is 4 pi here. From here to here, that full period. And what I did was I didn't have a whole one. So this was the mid, this was here, this was here, and this was here. That's a full period. And this was going from negative 2 pi to 2 pi. And that was the transformed function. They always go ahead and compare it to that parent function. And you notice it's going a lot slower here. It's going a lot slower. If I looked at the y equals cosine, it's going to be like this. So here, if I look at y equals cosine 2x, it's looking like this. Goes much more spread out. Much more spread out. So frequency, it's going to change the period. How long the period is. Next one, phase shift. Phase shift, all we're doing is moving it over. And I think the easiest way to look at this, where do I start? I start with y equals secant x. It's like this. That's one full cycle from negative pi over 2 to 3 pi over 2. pi over 2 to 3 pi over 2. I'm getting a full graph. Then if I move this over pi, I'm at here. Here I go over to here. And that is still the same period, 2 pi. But actually, this is minus pi, so it's moving to the right. This is going to move to the right. And this is that part. So I guess maybe I should just draw it. So these are moving to the right. Minus pi moving to the right. So this leg now is represented there. Next one, we're moving to the right only pi over 2. So I have this again starting, and it's easy to show. I moved it over to the right to get to the at pi over 2. They end up overlapping with the parent function, but that's okay. It's just, it needs to meet over only pi over 2. That's the right pi over 2. This over here was to the left pi. To the right pi, sorry. Both of them are to the right. So the right pi over 2 and to the right pi. That's the phase shift. The last thing we have is the vertical shift, which is even easier. But again, it's really good to go ahead and highlight these. I start off, these happen to be in green as the parent function. And I'm going to go ahead and say this is my midline. And then if I look at, if I move that midline up 1, now it's like this. So that's what's happened. I just moved everything up 1. Nothing else changed. It's just a regular old cosecant, except now we moved it up 1. The other one we moved down 3. So again, I look at 2 examples. Midline is right down the middle. Now if I go ahead, if I move that down 3, my midline is going to be here. And I have the same cosecant function, but it's off that other midline. Going up 1. So my local min here is -2. My local max here is -4. And I still go up to infinity overall for the function, down to -infinity for the whole function. But this is at 3, this is at 2, and this is at 4. That's going down to 4, and this is going up to 2. Instead of up 1 and down -. Okay. Put that in action. An example. Which one of these is y equals cosecant 3x? First of all, which one, if I look at this graph, if I look at this expression, or this equation, have I changed A, B, C, or D? Which one did I change? Think back at what we started with. It's not A, is it? A would be right here. It might be B, C comes after X, and D comes after X. So it must be B. I've changed B. I changed B to be 3, which means I changed the frequency. This is the frequency, which helps me determine, therefore, the period is 2 pi over 3. Remember, it's 2 pi over B. This is 2 pi over 3. In that case, if I look at these, where would I draw an asymptote? Right here at -2 pi, and right here at 0. There's another asymptote at pi, there's another asymptote at -pi. But as far as period goes, this period is not looking good. It's not looking good at all. This would be a whole period from negative 2 pi to 0. That means its period must be 2 pi. That's equal to 2 pi. Doesn't seem to be 2 pi over 3. And in fact, when we come over here and we start graphing asymptotes, there's an asymptote here, and there's an asymptote here, which is sort of hard to figure out where that exactly is. But I can tell that it is something between pi over, from 0 to something more than pi over 2, less than pi. I can buy that that's going to be 2 pi over 3. That is 2 pi over 3. That would be about where that asymptote would be. So I would say this is definitely my answer. Its frequency, it's quicker. The distance, the period is only 2 pi over 3, not 2 pi. Therefore, it's happening more often. You can tell this one's happening much more often than this one. This one, 1, 2, 3, 4, 5, 6. I have 6 and a little more of what I have there on top. Here I only have 2. I have 3 on the bottom. Here I have 1, 2, 3, 4, 5, 6, and a little more on the bottom. So it is happening a lot faster. In fact, it's happening 3 times faster. Questions? Here, what's the period of this? Well, what's my B? The period is determined by my B. What's the B? A is equal to 3, B is equal to 4, C is equal to 0, and D is equal to 0. So if B is 4, and we're talking about secant, so we're talking about a 2 pi period normally, we're going to divide that by 4. So pi over 2, and I simplify that. Pi over 2 would be my answer. You don't have this in your notes. It's not in your notes. But I thought it was a good example anyway. It's going to take up too much room for me to share it with you in the notes, but I did want to point it out. I didn't get rid of it. Okay, on to cotangent. We talked about cotangent a little bit earlier. Now, looking at this, the normal cotangent function is here. Negative slope, and my asymptotes are at 0 and pi. Now, what I do is I do a compression of that or a stretch of that. And then this one actually has a reflection, a negative. That negative means that it really, this is weird. This negative makes like a reflection vertically, a vertical line, like down the midline of this graph, you would flip it over. Or in this case, we normally have a negative slope. Now we're going to have a positive slope. And instead of only going out half and down 1, back a half and up 1, we're going to go the other direction, and we're going, when we go out at halfway, we go up 2. When we go back half, we go down 2. So it's actually stretching, and it's got that negative component, which made that negative slope a positive slope. The next one, we're going to have both are going to be negative slopes. We're going to start with the negative slope of the green graph. And then we look at, what do? We compressed. This is a compression, which means they call it flatter or closer together. And instead of going out, well, let's look at this. If I look at where my asymptotes would be expected to be, here I was going out 1, down 1, out halfway, up 1. Now I'm going down to that red line. I'm only going up half. I go halfway over it, and I go only down a half a unit. So it makes it more compressed. It's curvier. This one got stretched out and got skinnier. This one got compressed and got more curved. It's pretty cool. That's the one thing about math space when they do have you graph it. You can see that. When you drag the points, you can see how it makes it more stretched out or more compressed. I want you to do that. Okay. So, what does B look like? Well, B is going to make the frequency. Remember, the frequency which changes the period. Either making it more often or less often. We start off with the parent function as our baseline. And then we look at y, and this should be 2x. Y cotangent 2x. I don't know what it looks like in your notes, but this was cotangent of x, this is y equals cotangent of 2x. So in this case, I'm going to go ahead and make my period instead of pi, because remember, cotangent and tangent, the period is pi. Now it's pi over b, which is pi over 2. So now it doesn't take pi to get done, it only takes pi over 2. So what happens? We end up with 2 of these within the same area as what we normally have 1. So we have 2 repeats of it in the same span as 1. This one, it's going to go half as fast. Okay. She already left. Okay. Yeah, she's there. She's there. Let them know she's on her way. Okay, the next one. We have our normal period of 1 pi. Here, this is what cotangent of 1/2 x. This is going to change the period to equal not pi, but 2 pi. So from here to here is going to be 2 pi. So that's more stretched out horizontally, or it's taking less of them. You end up having 2 of those. In that same span, we normally would have 2 repeats of that, 2 cycles within that time. Here we're only having 1 cycle within that time. It's slowed down. So when they're talking about that, this is widened. I would say it's widened, or it's slowed down. Here, it got narrower, or it's slowed up. I mean, it's sped up. It's sped up. Oh my gosh. It's too fast. Speed up. So they sped it up in this case, they slowed it down in that case. The cycle was narrower on paper, here was widened on paper. Because this was less than 1, it widened. This was more than 1, it was quicker. And obviously the parent function, easy. Okay. Phase shift. That means we moved it left or right. So we start off with our normal cotangent function. Where do we go there? Negative pi over 2 means we move it to the right. Pi over 2. So this leg that I had just highlighted would move over to here. It just moves to the right. Moves to the right, pi over 2. Here we started here. And now we're going to move to the left, pi over 4. So that's going to be this one here to that leg that we just did. It's this one. We moved over this way, pi over 4. This one moved to the right, pi over 2. This one moved to the left, pi over 4. Now I'm just taking one cycle and showing you what it did. Obviously, it's still repeating every pi. We didn't change the period, so it normally would be every pi, you would have another leg, with each one of those is going to move over pi over 2. Questions? And the last one. This one brings up the idea of concavity. Have you ever talked about concavity, ever thought about concavity? What we're saying here is, when we start off with this function, the concavity here all the way down to right at that midline, it's concave up. And then it changes to concave down as it passes. And this is what we sort of think of as the center point of that graph. Well, now if I want to move it down one, now I move that down to here, and that concavity up is going to be this portion, and that concavity down is going to be this portion. So I moved it down one. So this was moving it down 1 unit. Looking at that same idea over here, that's my leg that I'm going to look at for my parent function between 0 and pi. This still has a full leg between 0 and pi, but instead of being here, concave up and concave down, it's going to be here. It's going to go concave up to there and concave down towards the right. Both of them have a negative slope. In fact, both of them have exactly the same shape. It just was shifted up. This one is shifted up 2 units. Pretty simple, hopefully. But you sort of have to know that it still has that same property. If you go over halfway, you go up 1 unit. If you go over halfway, you go down 1 unit because the amplitude is 1. Here, same thing. You're going over halfway, you go down 1. Over 1. Over back halfway, you go up 1. You still have those same points you could graph. Okay. Excuse me. What's the transformation of this cotangent? Well, first off, I need to recognize that this is my A, this is my B, C is non-existent, C equals 0, and this is my D. What does A do? It changes its amplitude. So the amplitude is 2. Well, the B is equal to 5, which makes my period equal to pi over 5. Don't forget, it's really tempting to make that 2 pi over 5, but cotangent and tangent have a period of pi. B, I divide the normal period by B, that's pi over 5. Remember, no phase shift. And the vertical shift is down 2. Down 2. So those are my transformations. I've looked at A, B, C, and D. How did it affect it? Amplitude became 2. Period became pi over 5 because B was 5. Frequency B was 5. No phase shift because C is non-existent, so it equals 0 in this case. Remember, C and D, if they're not there, they become 0. If A or B are not there, they're 1. Because A and B are factors, C and D are just separate elements. And then the vertical shift was down 2. What are the asymptotes? Well, cotangent, think about cotangent of x is at 0, at pi, at 2 pi, at 3 pi, so it's every pi. You could say the asymptotes have an equation x equals k pi, k being an integer. Well, hold on. They're actually an integer. Okay, so now what do we have? Now that's the normal. Now we need to divide it by b. It's every pi over 5. So we're going to have 0, pi over 5, 2 pi over 5, 3 pi over 5. And go on backwards as well, just like this one was. So when I write that equation, it's x equals k times pi over 5. That's going to be my asymptotes. All the asymptotes will be represented by x equals k times pi over 5. And look, I think, okay.